Good morning everyone. I am Priyadashini. I am doing my project under the guidance of Dr. Kalayarasi ma'am, and my topic is analysis of single and multi-server counters using MMC queuing model. Now introduction of queuing theory. A mathematical method for examining the waiting lines or queue is called the queuing theory. In systems where customers arrive at a random and waiting for service, it examines the waiting time, queuing length and service efficiency. In the real world, bank, hospital, train reservation counters, call centers, supermarkets and traffic systems and educational institutions and have a lines. So mathematical study of waiting lines or queue is known as a queuing theory. The introduction by A.K. Ireland at the beginning of 20th century, like industries, bank, telecommunication, healthcare and transportation and education. Next we go to MMC model is one of the most popular queuing models for multi-server systems like administrative counters with several counters, MM1 system with a single server, MMC multi-server system, MMCN multi-server with limited capacity. Symbol interpretation: M refers Poisson-Markovian arrival process, M refers exponential Markovian service time, C refers the quantity of service counters. Next we go to MM1 system mathematical model. MM1 mathematical model, following key performance matrix for a single server queuing system. MM1 queuing model make use of the following notations. Lambda refers the average arrival rate per unit time, mu refers average service rate per unit time, and C refers the server utilization. Rho formula is equal to lambda divided by mu. So LQ is a typical number of pupils in line, and LS the system average student population. WQ refers the mean amount of time spent in queue, and WS average amount of time inside a student spends using the system. Next we go to server utilization formula. Rho is equal to lambda by mu, and system's average number of student, LS is equal to lambda divided by lambda minus mu. Average number of students waiting in line, LQ is equal to lambda square divided by mu of mu minus lambda. And next formula is student average waiting time. WS is equal to 1 divided by mu minus lambda. Average queue waiting time is WQ is equal to lambda divided by mu of mu minus lambda. And next we talk about a single server. Assume a college has only one single inquiry counter where students come for certificate issue and general inquiries. Average arrival rate of students, lambda is equal to 10 students per hour. Average service rate of counter, mu is equal to 15 students per hour, and number of servers, one single server. Server utilization formula: rho is equal to lambda by mu. We substitute the value and we get the answer 0.667. So 66.67% the counter is busy of that time. And next, average number of students in system S is equal to 2. The average number of students in the system, 2 students, and average number of students in the queue or line is 1.33 students. Average number of waiting time in the student is 0.2 hours. We have to convert into minutes, so 0.2 equal into 60 is equal to 12 minutes. And next we go to average waiting time in the queue. WQ is equal to 0.133 hours. We convert into minutes into 60 is approximately 8 minutes. So the finding demonstrate of students spend a significant amount of time waiting in the system. It moderate utilization 66.67% and 8 minutes in the average wait time in the line, and through it could be go up during the busy times. And we have to see 3 counters. First one, registration counter. Registration counter, lambda is equal to 120 customers per hour, mu is equal to 50 customers per hour, and C is equal to 3 servers. Traffic intensity, lambda by mu is equal to 2.4. If server utilization, rho is equal to lambda divided by C mu. So system is utilized 80% of the time and servers are busy most of the time. So the queue is still stable because rho is less than 1. So rho value 0.8 is less than 1. So the queue is still stable. And next we have to see about the steady state normalization. P naught formula is there. I substitute n naught where n equal to 0, 1, 2, substitute these values and we get 6.28, and finally we get P naught value is approximately 0.05617977753. We approximately get 5.618 percentage, and compute the expected queue length. LQ is approximately 2.5888 customers, and total expected number in system in L is equal to approximately 4.9888 customers. And we see about the average waiting time in queue is 1.2944 minutes. Average time in the system is approximately 2.4944 minutes. And second one is examination form submission counter. Lambda is equal to 150 customers per hour, mu is equal to 60 customers per hour, and 3 is equal to 3 servers. Similarly, we same procedure apply. Traffic intensity is equal to 2.5, and server utilization 83.3 percentage. So system is utilized 83% of the time. So steady state formula is same, P naught value, and substitute this n equal to 0, 1, 2, and we get the P naught value is 4.494 percentage, and LQ is 3.51 customers, and L is approximately 6.0112 customers, and W is approximately 2.4045 minutes. And third one is inquiry certificate issue counter. Lambda is equal to 100 customer per hour, and mu is equal to 40 customers per hour, and C is equal to 4 servers. Traffic intensity A is equal to lambda by mu is equal to 2.5, and server utilization formula is rho is equal to lambda divided by C mu. We substitute the value of lambda, C, mu, and we get 62.5 percentage. So the system is utilized 62% of the time. And steady state formula, we know P naught value, we substitute these values to P naught, and we get P naught value is 0.0736949846, and we get the percentage 7.3695 percentage, and customers waiting on average 0.53 percentage, and total expected number of system L is equal to formula LQ plus A, so approximately 3.033 customers. So average waiting time in queue and average time in system, both formula have WQ is equal to LQ by lambda and L by lambda. We get 0.053 hours, we convert into minutes, 19.19 seconds, and W value is for 49.19 second. And finally we conclusion in this study, the performance of a single server, MM1, and multi-server administrative counters was analyzed using the queuing theory model with a given numerical values for arrival rate and service rate. The numerical results show that a single server system and the average waiting time and queuing length are relatively high, which leads to congestion and longer delays for customers. Therefore, the study concludes single server system are suitable only for low traffic conditions, whereas the multi-server system provides a better performance and efficiency under heavy traffic conditions. Hence, the administrative counters with a high number of customers and multi-server model is more effective and reliable. And we conclude about the multi-server system. We take a 3 counters: registration counters 1, and second one is inquiry counter, and third one is exam submission form counters. In these 3 counters, we have to find the traffic intensity and the server utilization formula. The traffic intensity for registration counter for 1 is 2.4. we get because we get the value already. We know about the lambda and the mu value. Lambda is 120 customers and mu is 50 customers, so we have to calculate or simplify 120 divided by 50. We get 2.4 customers traffic intensity, and server utilization is rho is equal to lambda divided by C mu. Lambda value is 120 customers, and C is number of servers, 3 servers, and mu is 50 customers. We simplify that, we get 0.8. We have to convert into percentage, so 8 divided by, so we get 80%. The system is utilized 80% of the time for first registration counters, and second one is exam submission form counters, right? So lambda value, traffic intensity lambda by mu. Lambda value is 150 and mu value is 60. We simplify 2.5 we get, and the server utilization rho is equal to lambda divided by C mu is equal to 0.83%. We conclude 83.3%. So the second form or second counter, the system utilized 83%, but for and lost a third counter. The third counter is inquiry certificate counter. Similarly, lambda value 100 and mu value 40. We simplify 2.5, get traffic intensity, and server utilization rho is equal to lambda divided by c mu. Lambda value 100 and mu value 40 customers per hour, and c value is 4 servers. So we get 62.5%. The system is utilized 62% of the time. So finally we conclude these three counters, and also we find single server. So we have to difference both a multi-server and single server. So in conclusion, we conclude that the single server system are low traffic conditions, but in multi-server heavy traffic conditions we have to wait in some time of queue lines, but in single server we have to wait in moreover minute or time hour per hour. So finally, we conclude the administrative counters, high number of customers, and multi-server MMC model is more effective and reliable. And thank you.